last year, when we have equation of tangent line, say your curve looks like that, right? So this is F. And then equation of the tangent line, let's say it's here at the point of tangency right there. Okay, and then we used to have something like this picture. So if I call this thing dx, which is same as delta x, and this is what we call dy, where this is what we call delta y. And then do you remember the differential idea? So what we had was, equation of the tangent line was this, right? You know what I'm saying? And then this two, we can call it delta y. And then that is approximately equal to this thingy. I'm going to call it dy over dx. And this is delta x, isn't it? Do you kind of remember that thingy? Right. This was called the differentials, right? It came out of the equation of the line. And after all, like limit of delta y over delta x approaching 0 is equal to dy over dx. You know what I'm saying? So that tells you that delta y over delta x is approximately equal to dy over dx anyway. And that's another way of looking at it. So we get this equation. Okay, now we are going to do the similar thing in 3D. Okay. And this could get a little complex, so let's pay attention. So if we have 3D, that's not very straight. Let me try that again. Okay, that's better. If you have some kind of 3D coordinate here, and then you have quadratic surface. My quadratic surface always looks exactly the same, right? Like that. And then here is a point of tangency. And then, of course, that point has then x naught, y naught, and z naught as a point. Now we are supposed to find the equation of the tangent plane touching right there. Okay, how can we do that? So suppose our plane looks like this. Like that. So far so good? You with me? Now, in order to find the equation of the plane, what did we need? It's like point slope form. So we need a point, and we have a point right here, and we need a normal vector, don't we? Say normal vector points that way at the moment. That's normal vector. Oh, hold on. That's a normal vector, let's say. You know what I'm saying? And that is perpendicular to this plane. So since we already have a point, now we have to go find that normal vector. How do we create normal vector? Okay. Let's just say in one direction, this x direction, let's say that is a vector, A. Okay. That vector A moves tangent to this thing. So this is a tangent vector of the curve. So it's contained in this plane. That makes sense to you? Like that. And I like to propose this is the size of this vector. I have 1 in x direction. So x movement is 1 and y movement is 0. And z movement is partial z, partial x. How about that? Oh, by the way, this equation is z is equal to f of some xy. That makes sense to you? So because the slope of this vector, as x moves by 1, the y will, in this case, looks like going down by that slope of the surface. That makes sense to you? Do you agree with this vector? Okay. Well, then we can create another vector in y direction. Say it's going that way, and we'll call that vector b. And that vector b, likewise, will have 0 and 1 in y direction and partial z, partial y, wouldn't it? And that's also perpendicular. You with me? Say yes. Okay, then now it's a downhill. So this normal vector n has to be then a cross b, eh? Say yes. Okay, a little technicality which I may, no, we don't have to. Okay, so then let's take a cross product. So cross product is done this way, I, j, k, and then a is 1, 0, partial z, partial x, and then y is 0, 1, partial z, partial y. Are we good? So what we get is this vector, I, this minus this, so negative partial z, partial x, and j is a negative 1. So we have this, and the other one is 0, so negative partial z, partial y, and k, this one, so you get 1. So far, so good. Now, after this point, we have to remember how to put the equation of the plane together. Remember, equation of the plane was done this way. Do you still remember this, or do you want me to go over that? And we calculated here. And then partial z, partial y, and 1. Dot product, and this r is basically x minus x naught, y minus y naught. See, this r has x, y, z in it. This one has x naught, y naught, z naught in it. You know what I'm saying? So if you subtract those two vectors, and this gives you what appears to be a point slope form. And this much is a review. This dot product is equal to 0, therefore normal vector is perpendicular to this thing, what becomes a plane. You with me? Okay, so taking dot products now. So I'm going to have negative partial z over partial x times x minus x naught minus partial z partial y of y minus y naught and plus c minus c naught is equal to 0. Good. Now, lo and behold, this remarkably looks like points law form in 2D. You have z minus c naught is equal to the slope in x direction plus the slope in y direction, and then y minus y naught. Wow, that's remarkable now, isn't it? You see, our point slope form earlier looked like that. So this, if you just block that out for now, and just this looks like a point slope form. But then if you look at this thingy and that thingy, it also looks like point slope form in 2D. And then you just put the combination of the two. And this is the equation of the tangent plane. Dang, huh? And also the differential, this we'll call it delta z or delta f, which is same as delta z. Now that's approximately equal to dz, just like before. And dz, of course, is equal to this. Partial z, partial x, and delta x where dx, delta x, let's call it dx, plus partial z, partial y, dy. And we use that for error approximation later. Good? Good, 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 good. Okay, before we go to this complex looking picture, let's take a nice concrete example first, okay? So let's push this thing down a little bit. And I'm gonna take this example. We want to find the equation, so this is example. Equation of the tangent line of tangent plane of this thingy. At 2, 1, 1. Oh, do you have this ellipsoid popping up in your back of your eyeball? Because we have done this, we have sketched this thing before, right? Okay, let's take this thing and calculate the equation of the tangent plane, okay? So we need partial derivatives first, and we'll of course do it implicitly. So taking a partial derivative with respect to x, so this thing becomes x over 2, good? This thing dies because we are holding y as a constant is with respect to x, plus, and this thing becomes 2z, and then chain rule. Remember this from last year, single variable calculus? And that becomes 0, so partial z, partial x is equal to negative, let's say, x over 4, right? Good. Now, while we are at it, we evaluate this at 2, 1, 1. Okay, and that gives you negative 1/2 a. You with me? I'll let you write that down. Okay, likewise, partial derivative with respect to y then. So this dies, and this gives you negative 2o. This computer always does that. This gives you negative 2y with respect to y, and this gives you plus. Did I write minus here? Oh, no wonder you look confused. That was plus. And then plus 2z, and the chain rule is equal to 0a. And that gives you partial z over partial y is equal to negative y over z. And while we are at it, we'll evaluate this at 2, 1, 1. So we have negative 1a. So far, so good? You with me? So equation of this tangent plane is z minus z naught, this thingy, 1, is equal to this slope in x direction. So we have negative 1/2 x minus that thingy minus 1, the slope in y direction, negative 1, times y minus that thingy. How about that, huh? Okay, and since I want to save time, I'm going to copy and paste the graph that I have in Dropbox Note. Let's look like this. So this equation, this thing is that purple plane. Good. Now let's talk about the differentials then. Okay. With the differential, so I copied and pasted this thing out of the book. Okay, let's take a look at this picture. I'm gonna enlarge it a little bit. So we have a curve. This is the surface that I had. My surface looked like this, remember? So it's a little upside down direction. And this is our point, x naught, y naught, z naught. The book calls it a, b, and then f of a and b. Now, if we move a little bit into x direction, and they actually move backward instead of this way, but that's your delta x right here, which we set it equal to dx, and we move a little bit to the y direction, delta y, which we set it equal to dy, and then there will be a difference gap. So this picture is analogous to this picture right here, right? dy versus delta y here. So same thing happens here. And then this is what we call dz, which is a change in the plane, tangent plane. And this thing is delta z. You know what I'm saying? So let's just think about that a little bit. So if you want to make this f of xyz minus f of x naught, y naught, and z naught, and that looks complicated, but that's just this thingy is what I'm calling df, which is df delta f, which is same as delta z. You know what I'm saying? Are we good? Okay, that thingy can be approximated with dz. Good. And dz, of course, is our function, the derivative, and then x minus x naught, and plus our derivative in y direction and y minus y naught. Kind of what we did in the example A. Are we good? So what we call differential, that this thingy is same as, and then dx, that x, we set it to be equal, plus, and then dy, isn't it? So this is what dz is. Good? Are we good? Now here's a scary symbol, okay? Did I switch the 3D to the, let's do the whole thing in 3D, shall we? Yeah, no wonder this looks weird. Oh, you want me to erase one of this? Yeah, I'm gonna erase one of the Z and then redo the whole thing. Because no wonder that looks confusing. This was 2D at the moment. Correct? Okay, now suppose then we have 3D function. And will it translate exactly the same way? Now we cannot even imagine this thing, but 3D functions, if you have f of x, y, z, right? Then can we do exactly the same thing we did up there? Yeah, sure. So in this case, if we have f of x, y, z minus f of x naught, y naught, and z naught, okay, that's what we call df now. It'll be exactly the same thing now, and the other side, it'll be with respect to x, x minus x naught, and slope with respect to, and now it like kind of loses its meaning because it's not even a slope. And then you just add another one. Do you see that? Do you see that? That's approximately equal to. So what we defined as a differential of df is this derivative with respect to x, and then dx plus derivative with respect to y times dy, and we have one more term here. How about that? You get it? It's kind of over the top, but it's a natural extension to 3D derivative, 4D, if you will, right? This is a 4-dimensional function. It's got 3 variables in x, y, z. And here's a scary, scary symbol. Now, this sure looks like a dot product now, doesn't it? So keep up, fly with me. Good. And they actually have a symbol for this thingy. Okay. And this, we can call it upside down del with f, this f, dot, and this, of course, is our dr, right? Tiny like x, y, z, d. And this symbol is a little weird, it's dangerous, is this. In an operator theory, this is called a differential operator, right? This itself has no meaning. This is kind of like our analogous to this thingy last year. You know what I'm saying? Differential operator. See, when we take a derivative, now we are in 3D space and we have some kind of 3-variable function. You can take a derivative with respect to time, or you can take derivative with respect to space. Derivative with respect to time is easy. That's just this, right? But space, this is 3-dimensional space, so it's not just dx, or it's not just dy or dz, right? Which one? Which direction do we take a derivative? All of it, like that. So it only has a meaning if you apply it to a function. Just like this itself didn't have meaning unless you have some kind of function, right? So it's called the differential operator. This thing is pronounced del, D-E-L-L, not the computer del, but okay. And some mathematicians hate this symbol. Some use it, but many use it, and our book uses it, so we'll use it. And this thingy, and this all together is known as gradient. Gradient vector. Okay, so if you take a differential operator to a function, scalar, then it gives you a gradient vector. And this thing actually points towards this direction. We'll talk about that direction of the gradient vector later. But it's like, you know, it's coming future, it's there. Okay. And have you done kinetic energy, potential energy thingy in your physics class yet? Have you done gravitational field versus the potential? Okay, then you can somewhat understand the relationship between this. It's more easier with the electric field, but you haven't done an E&M yet, right? So if you take a gradient of the potential, U, and this is a potential function, you're familiar with U, right? Potential energy kind of thing. And then what you get is the field, like gravitational field. And so this is a field. Oh, I know it's heavy, it's like way over the head, but for now, all you have to do is just do equation of the tangent line and practice that and take these partial derivatives. And then eventually we'll talk about this gradient vector. Okay.